This is one of the problems in your textbook. It asks you to draw reasonable resonance structures for the following ions. So that means every single possible resonance structure you need to draw. And to find the best, you need to calculate the formal charges. So pause the video, draw your structure, and then check your answer. So hydrogen has 1 valence electron plus 6 from the sulfur. There's 4 oxygen, each with 6. Since it's a negative charge, we need to add an electron. There's 32 electrons. Central atom, you know, is going to be sulfur. It's the least electronegative. Hydrogen does not count because it can only make 1 bond. Oxygens are going to be around it, and hydrogen is going to bond to the O. We're going to fulfill the octet and the duet rule. The hydrogen already has the duet rule. The oxygen next to the hydrogen needs 2 more pairs of electrons because it already has 4 from the bonded. The rest of the oxygen needs 6 more because it only has 2 from the bonded. Sulfur is in period 3 through 7. It could also have a double bond. So possible structures are HOS, and I'm going to start with a double bond on top. I'm going to fulfill the octet and duet rule. Hydrogen is happy with 2. The oxygen next to hydrogen only has 4 electrons from the bonded, so it needs 4 more. The double bond oxygen has 4 from the bonded, so it needs 2 lone pairs. And then the rest, since it has 2 electrons from the bonded, it needs 6 more. Since it has a double bond, the double bond could exist in any of the oxygens. So we're going to rotate the double bond. We're going to again fulfill the duet and octet rule. Since these are all ions, they all need brackets with a charge on the outside. And I need the double-headed arrows. Now I'm going to calculate the formal charges. Formal charge, Q is equal to the valence electron minus the lone electrons in the bonded pairs minus the bonded electrons divided by 2, or the number of bonds. So we're going to calculate hydrogen. Hydrogen is going to have 1 valence electron. It has 0 lones and has 1 bond, so it's going to be 0. Oxygen, in the first picture that is bonded to the hydrogen, is going to be 6 valence electrons minus 4 lones, 2, 4, and has 2 bonded pairs, so that's also 0. We're going to do sulfur in the first picture. That's going to have 6 valence minus 0 lones minus 4 bonds, so that's going to have a plus 2. And then the oxygens on the outside, it's going to have 6 valence minus 6 lones, 1, 2, 3, minus 1 bond, so that's going to have a minus 1 charge. In general, the hydrogen here is the same as before. The oxygen here is the same before. So the only thing I need to calculate in this picture is the double bond. So the oxygen that is the double bond is going to have 6 valence minus 4 lones, 2, 4, minus 2 bonds, which is 0. And then all the pictures are the same until we come back down here. We also need to calculate the sulfur. The sulfur in the central atom, 6 valence, 0 lones, and has 1, 2, 3, 4, 5 bonds. So this is going to be a plus 1. And then the only difference is this bottom picture for the oxygen. So that's going to be oxygen is equal to 6 valence minus 2 lones right here minus 3 bonds. So this is going to be a plus 1. Now I'm going to put the charges in. Hydrogen is going to be a 0 charge. Oxygen is going to be a 0 charge. The sulfur is going to be a plus 2 charge. Oxygen on the outside is going to be all minuses. In the second picture, hydrogen is going to be 0 again. Oxygen here is going to be 0. The sulfur in the center is a +1, and the oxygens are also 0. These bottom two will look exactly like the previous one. Last one, the hydrogen will be 0, oxygen will be a plus, the outside oxygens will all be 0, and the sulfur will be plus. The best structure possible are going to be these three right here. This one, the oxygen is negative, which you want because it is more electronegative, because it is least electronegative. On the bottom one here, sulfur is still positive. Majority of the oxygens are 0, but this oxygen, which is more electronegative, has a positive value. But if I look at the three resonance structures that I circled, everything is close to 0 or are 0, and sulfur has a positive value. Pause the video, try this problem on your own, and then check your answer. Phosphorus has 5 valence electrons. There are 4 oxygens, each with 6. It has a -3 charge, so I need to add the 3. So there is 32 electrons. Central atom is phosphorus. The oxygens are going to be around it. So we're going to start with a single bond. Each oxygen has 2 electrons, so I need to have 6 more. Phosphorus has 8. This is a possible structure. If I count, it matches 32 valence electrons. Phosphorus is in period 3 through 7. It could also exceed the octet rule. Start with a double bond. So the double bond oxygen can only need 4 more electrons. The rest needs 6 more. And since it has a double bond, the double bond can be rotated. Since these are ions, the brackets, the charge on the outside, and they are also resonance structures, so you need a double-headed arrow. So now I'm going to calculate the form of charge to see which is the most viable here. I'm going to start with the top left picture. Form of charge is Q, valence electrons from the periodic table, minus the lone electrons in the non-bonding pair, minus the bond electron divided by 2, or just the number of bonds. So the oxygen, 6 valence electrons. It has 6 lones, 2, 4, 6, and it has 1 bond, so it is a -1. All the oxygens are the same because they look the same. Phosphorus has 5 valence, minus 0 lones in the picture, minus 4 bonds, so this is going to be a +1. My next picture on the top right, the oxygens are going to be the same as before. I'm going to calculate the oxygen with the double bond. It's going to have 6 valence, minus 4 lones, 2, 4, minus 2 bonded, so this is going to be 0. We have to do the phosphorus. The phosphorus has 5 valence, minus 0 lones, minus 5 bonds. 1, 2, 3, 4, 5. This is also equal to 0. And the remaining pictures will have the same because they have the same structure. Now I'm going to put my charges in. So oxygen has a negative charge, all of these, and phosphorus has a positive charge. The more electronegative is negative in charge, the least electronegative is positive in charge. In the second picture, all the oxygens have 0 charge, the phosphorus has 0s, and everything else in the bottom row will be the same because the structure is similar. So for PO43 minus, this structure is not going to be likely because the other 4 structures are at 0. And if you put a triple bond, you're going to see that formal charges are going to be greater than 0. These 4 structures are the most stable structures for PO43 minus. Pause the video and draw the Lewis-Stahl structure for HSO3 minus, and then check your answer. Hydrogen has 1 valence electron, plus 6 from the sulfur. There are 3 oxygen, each with 6 valence, and since it's a negative charge, we must add 1. So this is 26 electrons. Central atom is sulfur. This is surrounded by oxygen. Since this is an acid, the hydrogen is gonna attach to the oxygen. Now we're gonna fulfill the octet rule. So the oxygen attached to hydrogen already has 4 electrons, so it needs 4 more electrons, or 2 pairs. The other 2 oxygens need 6 more because they only have 2 from the single bond. Sulfur has 6 from the 3 bonds, so it needs 2 more to fulfill the octet rule. And hydrogen already fulfilled the duet. So if I count the number of electrons, this is correct, or possible structure for HSO3 minus. Sulfur is in period 3. We can also have double bonds. So we're going to start with the double bond on top and then fulfill the octet rule. The oxygen attached to the hydrogen already has 4, so it needs 4 more electrons. The double bond oxygen also has 4 electrons, so it needs 4 more. And the single bond oxygen needs 6 more. And then the central atom has 8, so it fulfills the octet rule. But if we count the total number of electrons in the Lewis dot structure, there's 24, and we need 26 extra goes to the sulfur. Now we're going to rotate the double bond to the other oxygen. Sulfur will need a pair, because if we just do the octet rule, we'll be short 2 electrons. We can also rotate it to the one that is bonded to the oxygen. So the oxygen that's bonded to the hydrogen only needs a pair of electrons because it already has 6 from the bonded. Everything has the octet rule and hydrogen has the duet rule. But if I count the Lewis dot structure, I am deficient 2 electrons, so the remainder must go to the central atom sulfur. These are all ions, so we need a bracket and a charge on the outside, as well as double-headed arrows for the resonance. Now we're going to calculate the formal charge to see which structure is the most stable. Formal charge, Q is equal to the valence minus the non-bonding electrons in the bonded pair, or the lone electrons in the bonded, minus the bonded electrons divided by 2, or just the number of bonds. I'm going to start on the top left. I'm going to calculate hydrogen. Hydrogen has 1 valence, no lones, and 1 bond, so it has a charge of 0. This is the oxygen next to the hydrogen, which has 6 valence minus 4 lones. We have 2 here and 2 here, minus 2 bonds, or 4 electrons from the bonds divided by 2, which is 2. This is 0. The single bonded oxygens have 6 valence minus 6 lones, 2, 4, 6, and 1 bond, so this is a minus 1. The other oxygen is the same. Now we're going to calculate the central atom sulfur. 6 valence minus 2 lones from here. It has 3 bonds. This has a plus 1. In this top right picture, it is exactly the same, except for the oxygen with the double bond and the sulfur with the lone pair. So the oxygen with the double bond is going to equal to 6 valence minus 4 lones minus 2 bonds. This is equal to 0. The sulfur central atom here has 6 valence minus 2 lones minus 4 bonds, so this is also 0, and everything else is the same. Third picture is also the same. In the last picture, we only have to calculate the oxygen. So the oxygen, 6 valence minus 2 lones minus 3, and this is equal to plus 1. I'm going to write in the charges. So the hydrogen has a charge of 0. The oxygen has a charge of 0. The single bond oxygen is negative 1. The sulfur is a plus. Top right picture, the hydrogen is still 0. The oxygen is 0. The double bond oxygen is 0. The single bond oxygen is a minus. The sulfur is a 0. The bottom right will have the same charges as the top, so hydrogen is 0, oxygen is 0, the single bond oxygen is a minus, the double bond is 0, and the central atom is 0. The last picture, the hydrogen is again 0, the double bond oxygen is a plus, the sulfur is still 0, the single bond oxygens are minus minus. So the most stable structure is the structure that had 0 formal charges, or the ones that are closest to 0, with the most electronegative element with the minus, the least electronegative with the positive. The top left, the hydrogen and oxygen here are 0. The oxygens with the single bonds are negative, which makes sense. Oxygen is more electronegative. Sulfur is least electronegative and it's positive. However, if you look at the double bond, pretty much every single formal charge is 0. We only have one that is a negative, and it's the one with the most electronegative. So this structure is not as stable as this structure, the bottom left structure, which is a resonance structure of it. And if you notice from the previous problem, if we put a double bond between the oxygen that is bonded to the hydrogen, the formal charge of that oxygen is higher. It becomes positive, and that makes it not stable. So the best structure are these two right here, which are the resonance structure, the double bond. Pause the video, draw the structure for SO3 2-, and then check your answer. Sulfur has 6 valence electrons. There are 3 oxygen, that is 6 valence, plus 2 because it has a 2- charge. This is equal to 26 electrons. The sulfur is in the middle, and the oxygen will be surrounding in a single bond. I'm going to fulfill the octet rule for the oxygen. Sulfur has 6, so it needs 2 more. If I count the electrons in the Lewis-Dot structure, it equals to 26, so this is a possible structure for SO3 2-. Since sulfur is in period 3, it could also have a double bond. So the double bond oxygen needs 4 more electrons to fulfill the octet rule. The oxygen itself needs 6 more because it only has a single bond and 2 electrons. And so does the other oxygen. If I look at my sulfur, it already has fulfilled the octet rule due to the 4 bonds. If I count the number of electrons in the Lewis-Dot structure, it is less than 26. It is deficient by 2 electrons. So the remaining electron goes to the central atom. And sulfur can exceed the octet rule because of the empty d orbitals. So this is a viable structure for SO3 2-. Since it has a double bond, there are going to be 2 other resonance structure. Rotate the double bond and then fulfill the octet rule for each. And from the previous, we know that the sulfur, because it can't exceed the octet rule, and we must match the valence electron of 26. Again, I'm going to rotate the double bond and fulfill the octet rule for the oxygen. Sulfur again will get 2 more. And since these are all ions, they get brackets in the charge. Now we're going to calculate the formal charge to figure out which one is the most stable structure. Formal charge Q is equal to the valence electrons off the periodic table minus the lone pair in the bonded structures minus the bonded electron divided by 2, or the number of bonds. We're going to start on the top left. The single bond oxygen has 6 valence electrons. It has 6 lones electron minus 1 bond, so that's going to be a -1. The sulfur has 6 valence minus 2 lones minus 3 bonds, so it's going to be a +1. The top right, the single bond oxygen are going to be the same charge as before, so we don't have to redo it. The double bond oxygen has 6 valence, 4 lone electron minus 2 bonds, so that's 0. The sulfur has 6 valence minus 2 lones -4 bonds, so that charge is 0. And the remaining structures, they will have the same charge because they are the resonance structures of the top right one. Now I'm going to write in my charges. The oxygen here are all single bonds, so they're all negative in charge. When we calculated the formal charge, the sulfur had a positive charge. Structure is possible. The most electronegative is negative in charge. The least electronegative is positive in charge. If I look at the second picture, the single bond oxygen is still minus in charge. The double bond oxygen is 0 in charge. And then the sulfur is also 0 in charge. That means all the resonance structures of that picture will have the same charges. So the single bond oxygens will be negative, the sulfur will be 0, and the double bond oxygen will be 0. And in the last picture, the double bond oxygen will be 0, the sulfur will be 0, and the single bond oxygen will be negative. So here the most stable structure will be these three right here. Two of the elements that have a formal charge of 0, the most electronegative oxygen, have formal charges of -1, versus the first picture in which all of them have a formal charge higher than 0. In general, periods 3 through 7 can exceed the octet rule. A lot of times sulfur and phosphorus will have double bonds because it is a more stable structure, because their formal charge will be closer to 0 or at 0.